you see me? La 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 la. Okay, good. I will begin with a word of prayer. So, Dear Father, we thank you for this day. I thank you again, Lord, for these students. Pray with us today, help us to understand a little bit more about how to do energy analysis, Lord. In your name I pray. Amen. All right, so I need to start with a sort of slightly general, slightly theoretical discussion. This is concerning one-dimensional problem. One-dimensional conservative net force. All right, so in this particular case, or perhaps also in the case that you have more going on, but you can neglect the other dimensions in some sense or another, which is reasonable. You can analyze the situation by just looking at graphs of the potential energy. So let me kind of show you why that's true. Newton's law says that ma is equal to the net force, right? Okay, so if that net force is minus d, let's say, I guess I've been using phi, so I'll say d phi. I don't know, I guess I don't usually use phi here. Maybe I use capital phi. I'm going to use u. I usually use a capital U in this sort of context. Yeah, go ahead and close the door. As much as the parade of trash cans is interesting, it's help us to focus here if I get rid of it. Now, of course, if you look at this, this is really m dv dt, right? Plus du dx is equal to 0, where v is the velocity, right? And golly, you can multiply this thing by dx dt, and then you got yourself an m dx dt, dv dt, plus dx dt, du dx equals to 0, multiplied by the velocity. All right. And then if you just tilt your head and squint, you can see that, in fact, this is nothing more than the time derivative of 1/2 mv squared. And that's the time derivative of u by the chain rule. Oh, it's not locked, okay. Right, because if one-dimensional motion, you can rewrite the potential energy as a function of x alone, right? But then, of course, you got the derivative of a sum equal to 0. You can combine these things, and you just got what? ddt of 1/2 mv squared plus u is equal to 0. Now this thing, right, and technically u is a function of what? A function of x, all right? So what we're looking at here, this is the energy as a function of position and velocity. It's 1/2 mv squared plus the potential energy, which is, by the way, a function of x. This equation above says what? The time derivative of the energy is what? 0. What does that say about energy? It's conserved, but more specifically, the mathematics here, it's constant, right? If you go from different time to different time, you get the same energy if the net force is conservative. And that's the formula for it. So you can study possible motions, all right? You can study possible motions for such a system by drawing what's called a phase plane or a Poincare plane. And it's a very interesting application of basically just graphing and calculus, and it's a lot of fun. So let me just kind of walk you through that, how that works. So let's start out with, let's let the potential energy be, say, 1/2 kx squared. All right. Then your total energy function is what? So this gives you energy equals to what? Like 1/2 mv squared plus 1/2 kx squared equals to constant, right? Some particular number. Now if I graph that, right? If I graph such a thing in the plane where the coordinates are position and velocity, what do I get? Let's build up to that. Instead, let's look at a graph of the position versus the potential energy. Right? What's it look like? 1/2 kx squared is what? Just that, right? Not done too greatly, but qualitatively, this is what it looks like, right? Now, if I go right under here, right? Right down here, right under it, and I draw another graph, x, and this time the vertical direction is not going to be energy anymore. It's going to be velocity. I can graph possible motions of such a system by looking at this xv plane. So the way it works, right, is the solutions to such a problem, they're level curves of the energy, in fact. 1/2 mv squared plus 1/2 kx squared equals to a constant. Here, let's look at a specific one. For example, if I have energy E naught and it's like this, right? That energy level. What is the significance of the intersection of this green line with the red line, and what's the significance of the dotted lines? What's the relation between total energy and potential energy? Energy is equal to potential energy, right, plus kinetic energy. In this particular discussion, it's 1/2 kx squared plus, well, 1/2 mv squared. Kinetic energy is always 1/2 mv squared in this context. A little bit later, we'll talk about rotational kinetic energy. Then there'll be something else. You say, what has rotational kinetic energy? Well, I'm glad you asked. For example, this, right? It's rotational kinetic energy that does this. See, I'm storing the energy in rotational kinetic energy, and then it comes back. Oh, too long. So this, we don't know how to describe yet. Sorry, my kids broke my previous one. I'm just happy to have one again to play with. I just need an excuse. But anyway, I digress. No, I can't do tricks. Okay, now that we've settled that. I know that's your next question. Okay. Because you students are all the same. Sorry. Like so many Trump voters, you're very predictable. All right. That's okay. Today, we're going to make physics great again. Let's see here. Man, that worked in the calculus class earlier, too. It's like those words are some sort of unholy magic that twists people's minds. Weird. Strange. Okay, anyway, if only there was some more reasoned candidate who'd been a reliable advocate of our position for a longer time. Man, I wish I had somebody like that to vote for. Oh well. Okay. I mean, I forgot to bring my computer today. Oh well. I don't know what I'm talking about. All right. Look here. If the energy, if you pick this point right here, right, like this one, that x. What would the significance be? The potential energy, the red, right, would be above the energy. What would that say about kinetic energy? If the total energy is larger than the potential energy, how could you possibly have that? That must mean that the kinetic energy is negative. Otherwise, right, if I have that this number is smaller than this sum, right, and excuse me, it's equal, I'm sorry. If this is bigger than that, and that's positive, it must be that this is negative. But kinetic energy can't be negative. It's 1/2 mv squared. At its worst, it's 0. So this over here, the dot, 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 this is the forbidden region, all right? Imagine yourself a journalist 5 years from now. And you wanted to say something against the government. Right here. Right here. Right here. I'm sorry. 5 years is too long. 3 years. Anyway, so, I cannot, it simply is impossible to have this. What does that mean? That means that the motion, if the total energy is E naught, right, the motion is stuck right in here. Now that corresponds down here. Where do these points go to? These points go to down here, like this and like that. This is supposed to be symmetrical. Well, I tried. So the places where you have zero velocity are where you have what? Maximum potential energy. All right? The place where you have zero potential energy, right there, is where you have the maximum velocity. And the energy gets traded back and forth between the two. But what you got here is something like this. It's generally an ellipse. If you look at this equation, I've got a sum of two squares multiplied by positive numbers equal to a constant. That's an ellipse. So the energy levels for a spring mass, this is, by the way, the energy of a spring. The energy levels of a spring mass system, if you look at the position velocity plane, this is, by the way, the so-called Poincare plane, sometimes called the phase plane. They're ellipses, right? And so if I had a different energy level, this is E naught. If I had a different energy level, like, I don't know, this one, E1, well then that would have a smaller energy. So it would be something like that. If you start at rest, right? If you just have a spring sitting there, no friction, and you just start at rest, no velocity, what does it do? Nothing, right? It's very boring. It's like, just sits there. It's just this. And what happens? If you go higher, higher energy levels, you get larger and larger what? Ellipses, woo, down here, right? Until the spring breaks, right? But if you look at the equation, oh, sorry. That's I don't know. You got the idea. A little bit troubling. Okay. As you can see, my picture is a little bit. Sorry. Let's try to keep the three stooging to a minimum for the rest of the lecture. All right, so another example. Before I go on, though, did I solve any equations? Did I put any numbers in? No, not a one. This is a purely qualitative analysis. It allows you to get the big picture of what's going on without actually solving the equations, right? But you can tell what are the possible motions, even so. That's interesting, I think. How about this? If I had the potential energy as a function of x was something like, I don't know, here, let me come up with the graph first, and then we'll figure out what its equation should be. Suppose it was something like this. Woo, woo, zoom, like that. So these are most fun to give if you just give the graph to start with and then say, draw the phase plane under it. So, I mean, you can come up with a formula which has that as its graph. What would that be? Yep.
What did you call it? A phase plane?
Phase plane, yeah. Also called a phase plane sometimes.
That's a point here.
Poincare, yeah. Dead mathematician, pioneer of the study of chaos. These sorts of things are useful to study, like if you have a system and you just give it a little nudge, where does it go? You know, so if you study those sorts of things, that leads to the study of chaos, sensitivity to initial conditions. This is the right kind of tool set to start asking those questions about chaos. You know, butterfly flaps its wings in China, Donald Trump wins the primary, that sort of thing, you know? So, sorry, this is a Trump edition of this lecture. I stand by it. So suppose this is the potential energy. As a private citizen, of course, just so we're clear, as a private citizen. What do I have here? Oh, can you guys give me a formula which does that? I mean, I don't know. It would take at least like a cubic, right? There's negative x cubed is much more boring though.
Plus 3?
That's this.
Three?
Plus 3 is just this, sorry, or this.
Yeah, we have to.
Here, do I have to do everything? I have to do everything here. It would be something like, I don't know, like, you guys are absolutely spot on about the minus. So like minus x plus 2 times x times x minus 3 or something like that. For example, this formula would have that graph. Whatever. Okay, so then I can say, what are the possible motions? If that's the potential energy for the system, what are the possible motions of the system? All right. In particular, I can ask a very specific question. You know, if and let's suppose that this is like 3 joules. Just to be a little bit more quantitative here. Suppose that's 3. This is the 3 joule level. All right. I could ask a question like, suppose your total energy is 2 joules. And suppose you start at position -1. Describe the possible motion. So begin at x equals to -1 with 2 joules equal to E. Describe motion. So how would you do it? Well, basically just imagine I could draw 2 joules in here. That would be, we do it in a different color. Something like this, right? There's 2 joules. And I guess I should draw it like this. 2 joules. And I'm starting at -1, so it's, you know, it's somewhere like here, conceptually. I mean, either you're going to the left or you're going to the right. I didn't even give us that much information. It doesn't really matter. All right. Now I can plot that down here in the phase plane. Like so. So I've got 0 velocity here and here. My maximum velocity is happening when I have my minimum potential energy, right? So like the maximum of the velocity would be like here and here, something like that. So qualitatively, the phase, here's the energy level plot, something like that. By the way, if v is positive, what's the direction? V is equal to dx dt. V is positive, which way are you going? To the right, right? So I can even draw a little, I can think of this as a parametric curve, like so, right? And that's also true for this one, by the way. The curves for v positive all go to the right, and for v negative, they all go to the left. And that basically describes the spring going this way, and then that way, then this way, then that way, then this way, then that way, then this way, then you got the idea. So the same thing happens here. It's almost like it's a spring. The motion, it just goes back and forth between this point, whatever that is, like, you know, x1 and x2, whatever those are. If I had a more precise graph, I could give you a precise answer about the motion, but I can definitely say this much. The motion is bounded, you know, close to the initial point, right? Certainly within 3 units, give or take. Do you guys see the idea? Let's draw another energy level. What if I had another potential? What if I had net energy equals to -3 joules? Describe motion. I guess to be clear, I should tell you this is maybe the minus 2 joule mark. So minus 3 joules would be where? Somewhere down here, right? So forbidden, 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 forbidden. These all would imply negative kinetic energy. I have to have potential energy smaller or matching kinetic energy. The only place that's possible is over here. So basically, it looks something like this. And it just goes off to infinity. It's unbounded motion. It just keeps going and going and going off to the right. Or if it's coming in, it goes all the way to, that, let's call it x3, and then it bounces back out and keeps going back out to infinity. Well, wait a minute. It has to do this, right? I'm stuck with that direction, so if it starts at like here, right, beyond x3, but it's going to the right, it just keeps going to the right forever and ever. But if it's starting at this point, some point beyond x3, and if it's going to the left, yeah, make sure. If it's going to the left, what it does is it comes into here, and then it gets as close as x3 to the origin, and then it goes back on out to infinity. Yes, sir?
I'm really confused on how you know whether or not it's... What did you call like the dotted place again? Like it's not okay?
Forbidden?
Yeah, how do you know whether it's that or not? Like,
It's very simple. It's very simple. The given purple line is potential energy, right? Pick any horizontal line. If the horizontal line is below the potential energy graph, it's energetically forbidden because that implies negative kinetic energy.
Okay.
If it's above, you got motion.
So then with the green line...
Oh,
there also be-
oh yes, yes, yes. Thank you. Excellent, excellent. So forbidden in here, you see, the reason I drew what I did before is because I had a little bit more fine print. I was starting at x equals minus 1, right? If I didn't tell you that, if I said you started at x equal to like x3 or something, it would be different. Absolutely. So these are forbidden. But over here, yeah, you got motion again. Drop that down. Let's call this thing x4. There's also unbounded motion over here like that. So like if you had energy of 2 joules and you started at x3 going to the right, you just keep going off to infinity. If you're going to the left, you swing in, get as close as x4, and then swing back out again.
Why is the red line forbidden?
Why is the what?
The red line, why is that forbidden?
Oh, it's not forbidden. I was just setting the scale. I haven't even drawn that down there yet. What would that look like? Sorry, good question. It's not forbidden here. By the way, I don't universally use dotted as forbidden. So if you look at old solutions, don't read too much into dottedness. It seems like a good convention. I'm not sure I've universally applied that convention in the past. Just a warning. So this one is interesting, right? It's got like, what's that question?
It looks like a fish.
Yeah, it looks like a fish. So there's like that point special. This point is also special, right? It's still got like maximum velocities here and here, right? And so, yeah, it looks something like a fish. So that's kind of an interesting point, you see, because there's a very interesting point. This point right here, which corresponds to this, is what's called an unstable equilibrium. If you give it a nudge one way, motion's kind of bounded. If you give it a nudge the other way, off to infinity it goes, and it's not stable. You don't know what's going to happen. If you're here and you have a slightly uncertain initial speed, anything could happen pretty much, right? What's the difference? This point right here is what? Like that. That's a stable equilibrium. What's another example of a stable equilibrium? Right here, right? You leave a spring sitting on a table without friction and don't do anything to it. You know what? Nothing happens. Stable equilibrium. You do something like this. Yep. This is, this is an example of a unstable equilibrium. It's at the top of some sort of potential energy hill, right? And if you give it a little bit of nudge, it's going to go down. By the way, because the really cool thing is, if you think about U equals to mgy, right? If you think about the plot of that, what's it look like? It's very boring. It's just a line, right? So typically what happens is, in an actual problem, you don't really have this forever and ever for all y, right? It's mgy right up into the point you hit the table. There's some minimum y called the floor. So the actual graph for physical problems is kind of more like what? Like this, right? Or maybe you have a mountain. I don't know. So the floor is curved, but you'll always try to just go down. All right, I digress. One other important example, and then I will shut up about this. What's the potential energy? This is an example we haven't talked about yet, but the force of gravity. And we'll spend some time talking about this. So I'm just starting the discussion. But Newton's general law, universal law of gravitation, states that the force of gravity is G, m, m1, big M, over r squared. And so I'm just keeping it simple for today. Basically, the idea is you've got some big mass m. It's stuck at the origin, all right? And then there's something like a planet, m1 out here. The mass of the planet is way, way smaller than the mass of the sun, all right? So what that means is that makes this approximation valid, that the sun basically is unmoved at the center of the system. Well, then Newton's universal law of gravitation says in such a system, the force of gravity is attractive. Well, that's good to know. It'd be somewhat unsettling if I had to hold the marker like this for fear of it going off to the ceiling. Like the gravity just makes it fly off to the sky. That'd be weird. No, gravity is attractive, right? Of course, the gravity I'm talking about right now is the gravity from the Earth. Here I'm talking about the sun pulling on the Earth. Let me get back to that. So this is the direction of the force of gravity, right? And it's proportional to g m over r squared. I guess if I want to talk about the radial direction, I should say what? I should put a minus here, right? Because the radial direction would be, like this would be r hat, right? Agree? So what would if I could realize that the radial force is minus du dr, what would the potential energy as a function of radius be for this force? Neglecting the other parts of the motion, like the angular aspect of it, just focusing on the radial. Admittedly, there's vector calculus I need to do there to justify this as being a reasonable neglect to make, but it turns out to be reasonable. Again, I'll do that some other day when it's more relevant. That's what we're doing. So what's the formula for U? mgy. Yes. Well, I'm talking, this is the sun, this is the Earth, okay? So definitely mgy is not on the. If I was talking about Earth, right? If this was the picture, and that here was you, then yeah, mgy is sort of okay there. If I draw y as what? This distance, right?
Why is it
Calculus. Can you guys do calculus? I'm asking you to solve this very complicated differential equation. Gm1m over r squared. You can do calculus. I refuse to believe that you guys can't do calculus. I will not live my life that way. We will make physics great again. We will learn to do calculus today. I differentiate what? I mean, fine, get rid of the minus. du dr. If I make it an x, does that make it easier? Du dx is gm1m over x squared. What is u? If I make it an x, does that make it so you can do it? Okay, by now it's uncool for you to say it, so let me do it. Minus g m1m. I don't want to, I know you guys you've got a reputation to uphold. Let's see here. I'm just kidding, mostly. Agree? What about it? When you differentiate 1 over x, you get minus 1 over x squared, because the power drops by 1. Differentiation. Right? So, u of r is in fact minus g m1m over r. It's minus the reciprocal of the radius times a constant. Yes, sir?
You said, wouldn't it be, if you're dropping the power by 1, since that's -2, wouldn't that have to be -3 instead of -1?
But I'm integrating. I'm undoing the derivative. Given that du dr is equal to blah, find u. This is integration.
You just kept saying differentiate, and I was like...
I'm sorry. Yeah, okay, so if we can blame it on me, that will make me happier. So it is my fault, yes. But anyway, we can definitely all agree that this is true, right? Now that we have gotten past my inane Trumpisms and such. So let's do the energy diagram. Now this one's kind of special because does negative radius make sense? To those of you who are currently taking calculus 2, I'm sorry, it does not. You may have just been taught that you can identify r with minus r if you flip the angle by 180 degrees, right? You guys doing that right now? Forget about that. R is positive. In fact, r here is really the spherical radius, so truth be told, r is like the square root of x squared plus y squared plus z squared. So you should understand I'm abusing notation here. It's not the same r that you've been working with in Calc 2 lately. Okay? So the domain of this is non-negative, right? 0 and positive. What does the minus reciprocal look like? It looks something like this. All right? And it goes asymptotically to 0. And then you can talk about different energy levels. What do you have? You know, if I pick a particular energy level, I've got something like that, or like this, right? Or like this. So these, what? Say E3, E2, E1. Now, the actual motion isn't that, right? that wouldn't be a happy planet to live on, right? If part of its orbit goes to r equal to 0, that's where the sun is. Not cool, right? Actually, what happens is something more like this, right? I mean, they actually go to some minimum radius. But that involves the things that's not, I mean, in principle, energetically, they can go to here. It's just the details of the rotational dynamics don't make that happen. As I'll derive later, the orbits of planets around the sun are ellipses, right? So there's like a minimum distance they get from the sun. And then there's maximum distance. But you can also just analyze it in terms of energy. And it's so if your energy is less than 0, right? If the energy is negative for the system, for the planet, the motion is bounded, right? You've got a closed orbit. It comes back to where it started again. What happens if the energy is 0? I think I made my point. Okay, E equals to 0. It just is not a black hole. But the motion goes on and on and on. These cases give you what are called elliptical orbits. I can't spell elliptical apparently. Elliptical. Oh man. How do you spell elliptical? E-L-L-I-P, elliptical. Yeah. This is parabolic. Parabolic is very special. It's very probably impossible to realize in practice. That means it's really between the case where energy is positive and energy positive. What's that up here? Again, keep going and going and going. E greater than 0. This is hyperbolic. Hyperbolic orbits are not bound. If something's motion is hyperbolic, that means it could be extrasolar, or at least it will be soon. It just keeps going and going and going and going. It's not bound by the gravitational pull of the sun. So you need positive energy to do like extrasolar travel. And you can just take a given comet. You can tell if you can find out what's its speed, right? And you can find out how far it is from the sun. You can calculate its net energy. If its net energy is negative, guess what? You'll see it again, at least in principle. Sometime it's going to come back around. But if its net energy is positive, take a good look, because that's the last time you're going to see it. Right? It will just go off to infinity. I don't think it can even loop around. I think it just keeps going. Well, I suppose hyperbolic could do something like this. Like that. So maybe if this is the Earth, you'll see it once here, and maybe you'll see it again over here, but maybe just twice. It won't circle the sun. Yeah. It's parabolic. That's just a name. I mean, it's in between elliptic and hyperbolic. It's also not bound. The motion's not bound. It goes on and on. It's kind of like the fish one we had before. Anyway, that's all I got to tell you about that. So the remaining time, your questions. We have time remaining, right? So, yeah. I think this is really important, because in quantum mechanics, something interesting happens. The energies, like there's some allowance for these forbidden energies in quantum mechanics through something called tunneling. So like if you have two regions which are close together, you can actually tunnel from one place to another by going through these forbidden energy levels. That's actually a lot of what's behind semiconductor technology and stuff. So this is maybe the first step in that discussion of understanding semiconductor technology in terms of energy level analysis. This is the classical side of things. Quantum mechanics gets a little bit more interesting. Yes, sir. Or, yep.
I used a question on the homework.
A what?
On the homework.
Yeah, go ahead.
Homework 7.
Uh-huh.
One question was like some weight, some kilogram rock is attached to the string of a like foam triangle.
Uh-huh.
And at the
Oh, vertical. I guess I can't go wrong.
And it has to find like the velocity at the bottom.
Uh-huh.
The tension at the 45 and at the back.
Okay. So, what's that?
Has to be new problem.
Oh, it doesn't matter. Anyway, if I look it up, I'll get it wrong. So, let's see here. So,
I think the rock was like 0.26 kilograms and the rope was 0.55 meters.
who cares? Let's just talk about it. So this is L, and this is M. So the question then is, right, you want to say energy is conserved for this system, right? Okay, so this is a conservative system. There's no friction. There's no force which is acting on the system that's not a conservative force. I mean, you might say that you might worry that the tension was not a conservative force, but it acts perpendicular to the motion, so it can't do work anyway.
Aren't there friction pendulums at the very top? Just very.
Yes, that's true. Real pendulums have friction. You caught me. But unfortunately, we have no sorts of we have no way of quantifying that real friction of the pendulum pivot point here, so we have to neglect that. Yeah.
How do you quantify that lower?
We can talk about pendulums with friction, I suppose, but that probably belongs to the larger discussion of torsion and such, like rotational physics. This one we can do right now. Sorry. We need to figure out what's the potential energy before and after, right? So basically it boils down to this. Where do you want to make potential energy zero? You can do it wherever you want. I reject your answer at the bottom. I'm going to say potential energy equals zero up here for my convenience. You could go either way. You want to make it down here? I mean, we can do that, whatever. Here, I'll do it down here, fine. You have freedom to make the zero of the potential energy wherever you want. This thing I was just talking about over here, you could have just said, well, it's that plus 7 joules, right? And you could do that if you wanted to. Then the classification of elliptical and parabolic and hyperbolic would all be shifted. It's just a choice because you differentiate that away to get to the force, right? There's an ambiguity in where you set the zero for the potential. Totally a freedom we have. Okay, so with this choice, though, we can compare the initial energy to the final energy, right? The initial energy, there's some potential energy. Let's say H, right? Is it let go?
No, it just swings.
I know, but is it released? Is it released from 45 degrees?
Maximum angle is 45.
Maximum angle is 45, so
It like swings up to 45 and comes down.
Oh,
just doing this thing.
yeah, okay. So it would be,
Rest, it's not.
you could trade this for a problem where you release it from 45 degrees, it would be the same. But that's not the problem. Okay, fine, I gotcha. MGH is the total energy, right? Because that's the energy up here. But that's equal to what? 1/2 mvf squared, right? Where vf is the velocity at the bottom, where we have foolishly decided to make the potential energy to be zero. I don't know, it's not really that foolish. But the point here is you got to figure out what h is in terms of L and the angle. So you draw a picture that's better. My picture's not very good. Ugh. I'll get it right eventually. 45 degrees is more like this. So this... It's supposed to be a straight line. Grief, I need a ruler or something. Right, so this distance here is h. This is what? That's cosine of 45 times L, right? So if you take L minus L times cosine of 45 degrees, that gives you H. Now you can put the numbers in that you have and work it out, right? Because you know the angle, you know the L, and you just get to figure out the V. Well, tension, remember, let's see here. So the tension, what direction does the tension go? Yeah, let's see here. At the base of the swing, the tension's like this, right? Oh, T. And you've also got what other force? mg. Any other forces? No, that's it. Now, these have to give us mv squared over L. That has to be equal to T minus mg, right? That's the radial part of Newton's law. And I know that the radial component of the acceleration is v squared over r because of that calculation we did ages ago. So I can figure out what tension is, because you know the V from what we just did with the energy conservation, right? That is, in fact, to be more specific, I'm talking about VF, right? It's right here. So, being that I know everything else there, I can solve for T. Let's think about the other one, though. What about this one? If I draw the free body diagram, what do I have? Right, well, gravity, of course. I've got the tension, right? I've got mg like this, and that's it. What's the v there? 0. So I have m times 0 squared over L is equal to what? Tension, right? Minus what? You can't go wrong here, right? 45 is very kind. It papers over your inability to understand between vertical and horizontal angles. I'm not saying you specifically have that problem. I'm just saying the abstract student who's taking this problem as a possible. You do have this problem? No. Don't admit to that. Let's see here. Unless you're voting for Trump, in which case, please admit to it. Let's see here. T cosine 45 degrees. Sorry, I'm having too much fun. So that has to be the thing that's balancing the tension to give us a net radial force of 0, which I must have because, again, it's going in a circle. It's the end of a it's like at the very edge of a circular motion, but it's still part of a circular motion, so it still is bound by the v squared over r formula. Does that make sense? I mean, I can put numbers in, but I don't think it helps make it make more sense, does it? No. You guys have other questions? Yep.
Could you do number 8 on homework 7?
Possibly. It's physics, so I never really know until I try if I can actually do the problem. Let's see here. Doo-doo-doo. Doo-doo-doo-doo-doo. All right, let's see if we can figure it out. Which is this, homework 6 or homework 7?
7.
Describe the problem.
It was the one where there was like a roller coaster thing at the top of a ramp that was like height gauge, and then it went down like around a circular loop.
Is it just like a quarter circle?
It's called writing the loop.
Oh, riding the loop. Ah.
The question was what was the minimum radius?
I got you. This one.
Yes.
Let's see here. Without friction around the track, it starts from rest at point A at a height h above the bottom of the track shown, and it's, let's see here, treat the car as a particle. Okay, sure, why not? That's just a fancy way of saying ignore the fact that it's got wheels and other forms of energy, right? Like wheels have a rotational kinetic energy, much like the yo-yo I was showing you. So we're neglecting all that. So this is h. At what, let's see, what is the minimum value h in terms of r such that the car moves around the loop without falling off at B? 2. Through the power of your intuition, you have discerned it to be 2? Or like 2 is the answer? What is it? To what? 2.5. Why? I'm not just looking for answers in here, right? It's the journey, not the answer, that matters in some sense. So what you got to do is think about at the top point here, right? We don't want it to fall off. What does that mean? It's what? mv squared over r. Yeah, so let's think about this here. What do we got? We got tension? Not tension, listen to me. We've got gravity, right? That's what gives you the circular motion, right? And what else do you have? Oh, I'm sorry. You can always make h bigger, right? And then you do what? You go through the top of the loop faster, right? But if you have less than that speed, then gravity wins at the top, right? You don't stay on the circle. So the limiting case would be mg equals to mv squared over r, right? Okay. I got you guys. So that would say that v, I need speed what? M's cancel, right? Root gr, right? So what's the energy? Let's call this E1. So E1 must be equal to what? E1 is equal to, well, on the one hand, it's 1/2 mv squared, right? But it's more than just that. By the way, we are going to be very boring and again define the potential energy be 0 on the ground. That is not a necessary thing. You could put it to be 0 somewhere else. All right. What is the potential energy up here at the point B? Right. Yeah, mg times 2r. Now, why does he say 2r? Did you guys see that? R plus r to get up here, right? It's a diameter off the ground. Everybody see that? Now this is equal to what? Energy is conserved here, no friction, right? So mgh. Mass has got nothing to do with it. They cancels, right? If this problem told you the mass of the car, it's just to waste your time, right? They tell you the mass of the car? Nope. Good web assign. Good web assign. All right. So every so often they give you information you don't need. I guess I do that too. It amuses me. Because you guys will just, those of you who don't understand, you'll just do all kinds of random crazy stuff with the numbers. It's a source of endless amusement for me. Like, I'm just going to add these numbers. Others will be like, no, I'm going to divide them. And then like, I don't know, it's just, there's no telling what you'll do with the numbers. All kinds of random stuff, yes.
Why do you have them equal to the potential energy?
Because that's the total energy up here.
Okay.
E naught is mgh. And,
This is only for H.
well, I'm trying to use conservation energy to figure something out here. I forgot what I was trying to figure out, actually.
H.
Oh, H?
So much
Okay.
minimalized thing H, so the mass cancels.
Oh, yeah, masses cancel. Oh, but the v squared is what? So I've got 1/2 gr plus 2 gr equals gh. G. Yeah, 5 halves r is equal to h. Woohoo! I'm sorry, I seem to have solved your homework problem. Oops. But have I solved your test problem? That is the question we could ask. So do you guys understand how to do the other parts of this question now that we've done this, or no? Yeah, it then asks us to compute the radial and tangential acceleration of the passengers when the car is at point C, which is... So we're supposed to find the speed, radial acceleration, and tangential acceleration at C. All right, so we can do that, I suppose, at C. So first of all, to analyze speed and acceleration and radial acceleration versus tangential acceleration, oh. Interesting. So to figure out the speed, we can use what at C? How about this? mgr plus 1/2 mvc squared is equal to what? The total energy of the problem, right? You could set it equal to mgh, you could set it equal to 5 halves gr, whatever you want. Anyway, it's equal to mgh, fine. And you have enough information to figure it then out. So you can solve this for VC, right? They give you numbers in the problem for various things, right? Like in mine, I have h. I have h is equal to 3.30 r. All right. If h is equal to 3.30 r and r is 24 meters, then let's see here, VC will be, notice the m's cancel, that's beside the point. And I've got what? Square root of 2 g times h minus r, I think. Yeah. 2 times 9.8 meters per second squared. And that, I've got 1.30 times r, 24.0 meters, whatever that works out to.